Before watching this video, please complete animated tutorial 30.2 in Launchpad so that you have a nice overview of the role of the hormones insulin and glucagon in regulating blood glucose levels. In this video, we'll be focusing on the beta cells of the pancreas and how they respond to changing levels of glucose, and discuss two different cell types in the body that respond to the insulin released by the pancreatic beta cells, namely adipocytes or fat cells and muscle cells. Before moving on, please make sure you have your worksheet printed out so that you can be completing it as you're watching. But for now, let's just focus in on the cells that we need to worry about. Some of these cells should look familiar. We have the epithelial cells lining the small intestine of the gut, separating the gut lumen from the blood. In addition, we have the pancreatic beta cells that express and produce the hormone insulin. We have two cell types that respond to that hormone: muscle cells and adipocytes. At this time, pause the video and please draw into this diagram or jot into your notes the types of membrane transports that will allow glucose to move in and out of these cells. This is how I've depicted my membrane transport of glucose. In red, you have the active transporter, namely the sodium glucose symporter that allows glucose to move from the gut lumen into the epithelial cells lining the small intestine. In green and blue, I have two different forms of facilitated diffusion of glucose. In green is the transporter GLUT2, and in blue is the transporter GLUT4. I don't want you to worry so much about the numbers of those transporters. They are both types of facilitated diffusion, but it is important to recognize that they are different because the cells that they function in respond to glucose very differently. Let's consider what happens after a large meal containing a lot of carbohydrates. High concentrations of glucose is generated inside the gut lumen through the action of digestion and breaking down of glucose polymers. Lots of absorption of glucose takes place, and the glucose levels of the blood increase dramatically. Let's consider what happens to the pancreatic beta cell in those conditions. Pancreatic beta cells are characterized by their ability to make the peptide hormone insulin. I've depicted that hormone here as red dots inside specialized vesicles surrounded by a lipid bilayer. That is the state in which we find insulin when blood glucose levels are fairly normal before they become elevated. Remember that the pancreatic beta cell expresses the glucose transporter 2. It has a low affinity for glucose, meaning that when there are normal levels of glucose in the bloodstream, very little glucose manages to work its way into the beta cell. In addition, there is a potassium channel on the plasma membrane of the beta cell, which allows potassium to move out of the cell under normal conditions. Now, after that increased meal of glucose and the increased glucose in the bloodstream, the concentration of glucose becomes such that now, even though the transporter doesn't recognize glucose very well, it's low affinity, there's so much of it that plenty enters the cell. Through a variety of pathways, which you should all be very familiar with now, this glucose is converted to ATP. And so with increased blood glucose levels, the concentration of ATP inside the cell increases. ATP has a way to block the function of the potassium channels. And when these channels stop working, the ion gradient across the membrane changes. This leads to the fusion of the insulin-carrying vesicles with the plasma membrane. Let me draw that in a little bit more detail so you can see what I mean. Before blood glucose levels rise, insulin is trapped inside a lipid bilayer. After blood glucose levels have risen, that vesicle will fuse with the plasma membrane so that those two lipid bilayers essentially become one, and the insulin is turned loose to diffuse into the bloodstream. Let's consider what happens when that insulin reaches the adipocyte. The adipocyte, too, is experiencing high levels of glucose in its extracellular environment. Remember that it expresses the glucose transporter GLUT4, which has a high affinity for glucose, meaning that even when there are low levels of glucose, those glucose molecules can interact with the transporter and diffuse into the cell. However, there are very few GLUT4 transporters expressed on the plasma membrane of the adipocyte in the absence of a signal from insulin. When the pancreatic beta cell releases insulin and the insulin drifts and finds its way through the bloodstream to the adipocyte, it cannot enter the cell cytoplasm, and so it must signal through a receptor, a specific insulin receptor, on the plasma membrane of that adipocyte. Activation of the insulin receptor by the binding of insulin itself triggers a sequence of events inside the cytoplasm, which allows these vesicles in the adipocyte carrying GLUT4 transporters to fuse to the plasma membrane. This causes many more GLUT4 transporters to be placed on the plasma membrane of the adipocyte, allowing many more opportunities for glucose molecules to diffuse in. Once inside the cytoplasm, glucose is converted first to acetyl-CoA, and then that acetyl-CoA is used to build up fatty acids and triglycerides, which will build up in the lipid droplet drawn in yellow. If we go back to the big picture here, where we're considering multiple cells, keep in mind that the muscle cells also contain an insulin receptor, also hold GLUT4 transporters in vesicles inside the cell until they receive the signal from insulin. When insulin is released into the blood by the beta cells, many different cells throughout the body will take up glucose, decreasing the overall glucose concentration in the bloodstream fairly rapidly. This feeds back onto the pancreatic beta cells to decrease the levels of ATP in those cells and slowly decrease the amount of insulin that's being secreted into the bloodstream. In the case study that we will discuss on Tuesday of next week, we will consider two possible ways in which this pathway can go wrong. One, in type 1 diabetes, where pancreatic beta cells are eliminated from the body and therefore individuals stop being able to produce insulin. Or in type 2 diabetes, where individuals stop, for a variety of reasons, responding to insulin.